In this deck, we focus on a core quayside optimization problem where two decisions must be made together. Crane assignment decides which quay cranes should serve which vessel bays. Crane scheduling decides the time sequence of operations for each assigned crane. If you solve these separately, you often get plans that look good in isolation but fail when combined. Assignment decisions affect what schedules are feasible, and scheduling decisions affect whether the assignment actually delivers throughput. The goal of an integrated approach is to optimize overall terminal performance while respecting the physical realities of crane movement, safety clearances, and varying handling times across bays. The scenario is a new automated terminal operated by the Port of Singapore Authority. The terminal has 12 state-of-the-art Quay cranes, serving a 1,200-meter berth that can accommodate 3 large vessels simultaneously. The terminal targets a throughput of 180 containers per hour per crane. Each vessel arrives with a specific bay configuration, different load distributions across bays, and tight departure schedules. The operational challenge is to coordinate assignments and schedules so cranes stay productive while the terminal still respects safety rules and non-crossing constraints. We solve the integrated crane assignment and scheduling problem through multiple tiers. Tier 1 provides a full integer programming formulation to define the complete model with all key constraints. Tier 2 uses a constructive heuristic called earliest available crane and shortest processing time. Tier 3 applies a genetic algorithm with specialized operators that preserve feasibility. Tier 4 uses deep reinforcement learning for adaptive decisions in a dynamic environment. Tier 5 integrates the optimization into a digital twin that synchronizes with berth, yard, and transport systems. Tier 6 explores an autonomous multi-agent ecosystem. Tier 9 introduces a quantum approximate optimization algorithm approach. Tier 1 builds a complete integer programming model that captures both assignment and scheduling decisions simultaneously. The model chooses which crane serves which bay and when, and it tracks completion times for each bay and each vessel. The objective combines multiple goals through weighted terms. It penalizes lateness relative to due dates, it can penalize earliness when early completion creates inefficiencies, and it also includes a term to reduce overall completion time. This creates a flexible objective that can reflect service commitments and productivity goals. This slide defines the main sets: vessels, cranes, bays for each vessel, and time periods in the planning horizon. Processing time for each bay captures how many time units of work are required. The model also includes vessel due dates and arrival times, plus a minimum clearance distance between cranes. Operationally, that clearance distance represents safety and interference rules that prevent cranes from working too close together. Decision variables represent whether a specific crane serves a specific bay of a specific vessel during a specific time period. Additional variables track whether a crane is assigned to a vessel, the completion time of each bay, and the completion time of each vessel. The model also uses variables for earliness and lateness. Operationally, these variables translate schedule outcomes into explicit penalty terms, which makes trade-offs between speed and due date performance measurable. The objective is a weighted combination of lateness penalty, earliness cost, and completion time minimization. Operationally, this reflects what terminals actually care about. Lateness is expensive because it risks missing sailing windows and customer commitments. Earliness can also have a cost if it causes resource imbalance or shifts work into a period where downstream systems are not ready. Completion time terms keep the overall plan efficient. The bay coverage constraint ensures that each bay receives enough crane time to cover its required processing time. Operationally, this prevents an infeasible plan where a bay is assigned a crane only briefly and then left unfinished. Each bay must get the full amount of work required to complete its container moves. Crane capacity ensures that each crane can work at most one bay at a time. Operationally, this prevents double booking. A crane cannot simultaneously serve 2 different bays in the same time period. Non-crossing constraints enforce a key physical rule. Cranes share a rail and cannot pass through each other. Operationally, if crane 1 is to the left of crane 2, the schedule must respect that ordering across time. This constraint is what couples spatial assignment to temporal scheduling. Clearance safety constraints enforce minimum separation between operating cranes. Operationally, this reduces collision risk and interference. Even if cranes do not cross, they still need safe spacing while working. Completion time logic defines when each bay is finished, based on the last time period in which it is served. Vessel completion is then the maximum completion time over all its bays. Operationally, this is how the model links micro-level work on bays to macro-level vessel turnaround. A vessel cannot depart until every bay's work is complete. This slide provides a visualization of the integrated mathematical model. Use it to connect the variables and constraints to the physical Quay. You are coordinating cranes over time across bay positions while respecting non-crossing and clearance rules. This example considers 2 vessels, 3 cranes, and 4 time periods. Vessel 1 has 2 bays requiring 2 and 3 time units. Vessel 2 has 2 bays requiring 1 and 2 time units. A feasible optimal plan assigns crane 1 to vessel 1 bay 1 in periods 1 to 2, crane 2 to vessel 1 bay 2 in periods 1 to 3, crane 3 to vessel 2 bay 1 in period 1, and crane 3 to vessel 2 bay 2 in periods 2 to 3. The reported total completion time is 6 periods while respecting non-crossing and clearance constraints. Tier 2 introduces a constructive heuristic designed for speed. It assigns tasks incrementally by selecting the earliest available crane and pairing it with the shortest processing time task that is feasible. Operationally, this is a greedy method with a look-ahead flavor. It keeps cranes busy, but it must constantly check feasibility under rail and clearance constraints. This slide shows the flow of the EAC-SPT heuristic. Maintain a queue of tasks by processing time, track crane availability, select the earliest available feasible crane, assign the next task, and update the schedule. Operationally, the flow reflects a real dispatch loop. Each assignment changes which cranes are free and which tasks remain, so the algorithm updates continuously. In the first code section, you typically see initialization of tasks and cranes and construction of the priority order by processing time. Operationally, the key detail is how you represent bay positions and how you ensure that candidate assignments respect non-crossing and clearance. This section usually performs the main assignment loop, choosing a crane and a task at each step. Operationally, it is not enough to choose the earliest available crane. You must choose the earliest available crane that can physically reach the bay without violating ordering constraints with other cranes. This section typically updates crane availability and task completion state. Operationally, these updates are what prevent conflicts later. If you update availability incorrectly, you create a schedule that looks feasible step by step but breaks when cranes interact. This final code section often reports schedule metrics such as utilization and make span. Operationally, these metrics let you compare the heuristic to stronger methods. Utilization tells you how much the cranes were kept productive. Makespan tells you how long the schedule took to finish all work. This slide reports a 6-vessel, 4-crane example where tasks are processed in a short processing time order. The schedule achieves 85% crane utilization with a total makespan of 4 time units. The lesson is that simple, greedy construction can produce strong schedules quickly, especially when the instance is structured and constraints do not cause excessive blocking. Tier 3 uses a genetic algorithm to explore a wider space of integrated schedules. Unlike a pure heuristic, it evolves a population of solutions through selection, crossover, and mutation. Because this problem has strict feasibility constraints, the genetic algorithm uses specialized operators designed to preserve constraint structure. That prevents the population from collapsing into infeasible schedules. This slide visualizes the genetic algorithm evolution loop. Create an initial population, evaluate fitness, select strong candidates, apply crossover and mutation, and repeat over generations. Operationally, you should interpret this as a controlled search that balances exploration of new schedules with exploitation of the best schedules found so far. In this first code section, you typically see how chromosomes are encoded and how initial feasible schedules are generated. Operationally, encoding matters because it determines what kinds of changes crossover and mutation can make without breaking feasibility. This section usually defines fitness computation based on makespan, utilization, and penalties for any constraint violations. Operationally, fitness must be aligned with what the terminal values. If it rewards only makespan, it may create unstable schedules. If it penalizes constraints too weakly, it may accept infeasible solutions. This section often defines the crossover operator that mixes parent solutions. In this problem, crossover must preserve the relative ordering of tasks on cranes and avoid generating non-crossing violations, which is why specialized operators are used. This section typically defines mutation, often as a controlled reassignment or a swap, followed by a repair or local improvement step. Operationally, mutation is what keeps diversity. Without it, the population can converge too early and miss better integrated schedules. This section usually contains the main evolutionary loop, including elitism so the best solutions are not lost. Operationally, elitism gives stability. You maintain a guaranteed best solution while the rest of the population explores. This slide reports a benchmark instance with 8 vessels, 6 cranes, and 24 bays. The genetic algorithm runs for 500 generations with a population of 100. The initial population has an average make span of 47 time units with 68% crane utilization. After evolution, the best solution reduces make span to 32 time units with 89% utilization. That is reported as a 31% improvement in efficiency. Tier 4 uses reinforcement learning to make integrated decisions sequentially. The agent observes the system state and chooses assignments and scheduling actions over time. The state includes vessel status and remaining workload, crane positions and availability, bay completion status, and the queue of pending tasks. Actions assign a crane to a task, schedule timing, or choose to wait. The reward trades off multiple effects: reducing make span, reducing idle time, increasing throughput, and penalizing constraint violations. Operationally, reward design is how you tell the agent what matters most. If constraint violations are not strongly penalized, the agent will learn illegal actions. If idle time is not penalized, it may waste cranes. This slide summarizes the deep queue network approach for learning assignment and scheduling decisions. Operationally, learning is done in simulation. Once trained, the policy can make rapid decisions online, which is useful when vessel arrivals and conditions vary. In the first pseudocode section, you typically define the environment state representation and initialize the network. Operationally, you must include the key feasibility information, especially crane ordering, clearance constraints, and bay positions. Otherwise, the agent cannot learn correct behavior. This section usually covers action selection with exploration. Operationally, exploration should be constrained to feasible actions and training. Infeasible actions should be masked or heavily penalized so the agent does not waste learning capacity. This part typically stores experiences and samples mini-batches for training. Operationally, replay helps the agent learn from rare but important congestion and conflict cases. This section often contains the training update step. Operationally, stable updates matter because unstable learning can produce oscillating policies that are unsafe in deployment. This section typically includes target network updates and training stabilization steps. Operationally, these techniques prevent divergence and help the learned policy converge to a consistent decision rule. This section often logs performance and checks convergence. Operationally, you want not only high reward but consistent feasibility and strong utilization across many scenarios. This final pseudocode part usually evaluates the learned policy and prepares it for use. Operationally, evaluation against rule-based baselines is essential before trust and deployment. This slide reports training on a dynamic environment with 10 vessels arriving over 24 hours. After 5,000 episodes, crane utilization rises to 92%, and average vessel turnaround time drops to 4.2 hours. The baseline rule-based approach achieves 73% utilization and 6.8 hours turnaround. The learned policy prioritizes urgent vessels during peaks and load balances during normal operations. Tier 5 integrates Quay crane scheduling with berth allocation, yard management, and truck or automated guided vehicle coordination. Real-time synchronization uses an event-driven architecture with microsecond precision timestamps. Each crane decision triggers updates to yard schedules, truck dispatch, and berth windows, enabling system-level consistency. This slide emphasizes integrated simulation and optimization across terminal subsystems. Operationally, the twin allows what-if experiments and predictive optimization that include downstream impacts, not just Quay crane metrics. This example describes a Rotterdam-style digital twin that processes 847 real-time data streams. When vessel A arrives 3 hours early and vessel B may be delayed, the twin reallocates berths and redistributes 6 cranes across 4 vessels. It also updates yard schedules and truck plans to match the new timeline. Reported outcomes are a 12% throughput improvement and a reduction in average vessel waiting time from 2.4 hours to 1.7 hours. Tier 6 moves to decentralized control. Each crane is an agent that bids on tasks based on position, workload, and predicted efficiency. Auction mechanisms and reputation systems reward reliability and penalize violations. Emergent behavior includes load balancing, dynamic crane clustering, and self-healing when a crane fails. This slide emphasizes that cranes, vessels, and subsystems negotiate to create emergent optimization without a centralized dispatcher. Operationally, the benefit is resilience. If one component fails, the rest of the ecosystem can renegotiate and adapt. This example describes a peak period with 5 vessels. Crane Agent 2 forms a coalition with Crane Agent 3 for a complex multi-bay job. Crane Agents 1 and 4 bid competitively for priority containers. When Crane Agent 3 detects mechanical issues and reduces its capability, nearby cranes rebalance and vessels renegotiate priorities. Reported efficiency reaches 94% of the theoretical centralized optimum, with improved adaptability. Tier 9 introduces quantum approximate optimization. The idea is to encode assignment and scheduling decisions in a binary formulation and optimize a quadratic objective with penalty terms for constraints. The algorithm alternates a cost operator and a mixing operator across multiple layers to search the discrete decision landscape. This slide describes encoding the integrated assignment and scheduling problem into a quadratic, unconstrained binary optimization structure. Operationally, the purpose is to represent discrete choices and constraint penalties in a form suitable for quantum optimization procedures. This slide describes the alternating operators used in a quantum approximate optimization algorithm: a cost operator tied to the objective and a mixing operator that explores the space. Operationally, these operators define how the algorithm moves through candidate schedules. This slide shows the quantum circuit structure that alternates those operators. Operationally, circuit depth represents how many alternations you use. More depth can improve solution quality but increases computational difficulty.